Welcome to next lecture of compiler design, that is on basic block, flow graph, optimization of basic block. So, I am Dr. Parul Yadav, assistant professor at Department of Computer Science and Engineering in Institute of Engineering and Technology, Lucknow. In today's class, we will cover basic block, next use information, our flow graph, then optimization of basic blocks using DAG representation. So, in a basic block, what is actually basic block? Up to previous class we have discussed the intermediate code, and we have obtained the intermediate code using 3 address code representation. We also talked about quadruple, triple, indirect triple and all. So, broadly we can say we know how to write intermediate code using 3 address code representation. Now, what is basic block? Here the idea is it provides the graphical representation of intermediate code. So, here we will be having 3 address code statements and we will write it graphical representation. Why are we doing so? It is done to provide better registration allocation by knowing how values are defined and used. Second, it provides better instruction selection by looking at the sequence of 3 address statements. So, for better registration allocation and instruction selection, we prefer to use block representation. Now, broadly we can say what we will do over here. Here we will partition the intermediate code into basic blocks, which are maximum sequence of consecutive 3 address instructions with the properties. Now, there are 2 properties. Properties are flow of control can only enter the basic block through the first instruction of the block, that is there are no jump into the middle of the block. Now, second is control will leave the block without halting, branching except possibly at the last instruction of the block. Now, next is here the basic block become the nodes of the flow graph and whose edges indicate which block can follow which other block. So, this representation will be used in designing the flow graph, where these blocks will represent the node and we will find that which block will come after the which block. Now, specifically we can say what process will follow. Here we will break the sequence of 3 addresses code into basic blocks. So, we will be having many 3 address code instructions. We will break the sequence into some block. Now, in the absence of begin a new block with the first instruction and keep adding the instruction until we meet a jump, conditional jump or label to the following instruction. So, we will start from the first statement and we will put the first statement in a block and we will keep on adding the statements in the block till we are meeting jump or conditional jump type statement or label type statement. Now, in the absence of jumps and labels, control proceeds sequentially from one instruction to the next. Now, here sequence of consecutive statements which may be entered only at the beginning and when entered next are executed in sequence without halt or possibility of branch. Now, here we will see one example to understand the concept how we will design the block. So, we will see one example, we will see what is the algorithm to design to obtain or construct the block. Now, suppose we have the source program, this is the beginning, here this is a assignment product is equal to 0, I is equal to 1, then this is the loop, while loop. So, do while loop, do begin, product is equal to product plus ai into bi, I is equal to I plus 1 and while I is greater than or equal to 20. I is less than or equal to 20. So, this is our source program and for that source program we can write the 3 address code. So, we already know how to obtain 3 address code for the given program. So, here we have the program it would be in any language and here this is the 3 address code representation. So, here we have 11 statements. One is the product is equal to 1, then I is equal to 1 and then here we have the word size, that is 4 word memories are required. So, to store single word. So, here T1 index is T1 is equal to 4 into I. Now, T2 is equal to address of A minus 4. Now, T3 is equal to T2 at T1. Similarly, we will compute T4, that is address of B minus 4, and T5 will be this for this T4 at T1. Now, T6 is the multiplication of these two, mean T3 and T5. Now, we are adding it into product. So, this is this. Now, we are increasing the counter, and for the while loop we are checking if I is less than or equal to 20, we will go to this particular statement, and here we will have the loop. So, this is the 3 address code representation for the given program. Now, we will see what is the method or algorithm for obtaining the block. So, what is the input to this algorithm? It is a sequence of 3 address code statements. So, we will have the sequence of 3 address statements like this. For any program we can have. Now, output will be the list of basic blocks with each 3 address statement in exactly one block. So, here we will obtain as output basic blocks. Now, what will be the method here? We will determine the set of leaders. So, we will determine the set of leaders. Second, we will construct basic block for each leader. So, these are the this is our method. Now, I will explain the method. So, first is to find the leader. So, how we find the leader? This is the 3 address code that we have. So, there are 3 steps to find the leader, or 3 approaches, 3 steps to find the leader. First statement of a 3 address code is a leader. So, we will say the instructions, the statements, 3 address code statements, 3 address statements, and here the first statement will be considered as leader. So, this product is equal to 1, it is a leader. Now, second is next will be the target statement of a conditional or unconditional go to is a leader. So, we will see here what is the target statement for conditional or unconditional go to. So, if you look at the statement here, this is first leader. Now, we will proceed, we will look at the target address of any go to, and here we have go to and the target address is 3. So, this 3 will be the leader, 3 will be the next leader. So, this is the second approach, second part of finding leader. Now, third way is statement that immediately follows a conditional go to is a leader. So, here we have this statement and a statement just after to it, suppose this is 12th statement. So, that statement will act as a leader. Here this is, we have not written any statement, otherwise this would have a will give us a leader. So, these are the 3 steps. First statement is a leader, target statement of any go to is a leader, and statement just after any conditional statement, conditional go to statement is a leader. So, in that way we will find all leaders. Now, second step is to build the blocks. So, here this is our code, here we have marked all the leaders. Statement 1 and in statement 3 they are the leaders here. Now, we will construct the basic block. So, we will construct basic block for each leader. So, each leader will lie in one block. So, how we will do? The basic block consists of the leader and all statements up to but not including the next leader or the end of the program. So, we will start to make the program. So, suppose we are making a block. So, here this statement will lie in block 1, this will also lie in block 1, and this is the start of second leader. So, block 1 will be like this. So, here it will have 2 statements, first and second, and this will be block 1. Now, next is this is a leader, and till we will search for the next leader, here no next leader. So, we will, and this is showing the end of the program. So, this whole will be in second block. So, this is the block 2. So, this is the fundamental method for obtaining the basic blocks. Next, we will discuss next use information. So, here what we have, knowing when the value of the variable will be used next is essential for generating good code. So, if we want to generate a good code, so we can say we need to know the value of variable, which variable value of the variable will be used next. So, if the value of the variable that is currently in the register will never be referenced subsequently, then that register can be assigned with another variable, right. Now, there are certain examples. Suppose we have one instruction, one statement that is I, and in this statement I assigns a value to x. So, this is I, and here suppose we are assigning value to the x variable, suppose it is 20. Now, statement j has x as a operand. So, there is one statement j, and here we are using this x as operand. Let it be like this, and control follows from I to j. Control is following from I to j along the path that has no interleaving assignment or to x. Now, this implies that statement j uses the value of x. J uses value of x that is computed in this particular statement, right. So, this is called as x is live. This x is live at statement j. In this statement, in this statement x is live, right. So, x is live. So, determine in I, sorry, in I. So, determine for each 3 address statement like this what the next uses of x, y, z are within the block. So, here we will find what is the next use of particular variable or particular statement. So, there is an algorithm to find the liveness or liveness and next use information. So, input is the basic block, right, B of 3 address statement. Here we assume that the symbol table initially shows all non-temporary variables B as being live or exit. Now, output will be at each statement I like this in B, attach I the liveness and the next use information of x, y and z. So, output will be we will tell whether it is for next use or not. So, method will be start at the last statement in B and in scan backward to the beginning of the B. So, we will start from the last statement and we will proceed till the beginning of B, and in B we contains all 3 address statements. Now, for each statement in B we will do these 3 steps. So, steps are attach statement I, the information currently found in the symbol table regarding the next use and liveness of x, y, z. Next, in the symbol table set x to not live or no next use, while in the symbol table we will set y and z as live or they are of next use. So, this is the algorithm for next use information. So, till now we discussed about basic block and the next use information. Now, next we will discuss the flow graph. So, flow graph tells that which block will be executed next. So, to portray the basic block and their successor relationships by a directed graph, we use the flow graph. So, here first of all for 3 address code we will obtain all the basic blocks and then we will check what is the flow of it. So, for this these are the blocks, and in flow diagram these blocks represent the nodes. So, this is the node. Next is initial block is the block that contains whose leader is the first statement. So, we are having the instructions and in the instruction this is the first statement, and the first statement this will be a leader and this will be lying in some block. That block will be considered as initial block or initial state we can say. Now, next is we need to know what is predecessor or successor. So, the block suppose we are talking about B2. So, with respect to B2, B1 is predecessor of B2 and B2 is successor of B1 because B2 is coming after B1. So, flow is like first we will execute statements in B1 and then we will execute statements in B2. Now, next we may be having loop also. So, every loop will have the unique entry and it is actually a strongly connected part. So, what is the flow graph for it? Here we have the instruction, this is the block and this is the block, and instruction sequence is like this. So, and we know that here we have some loop part also. So, flow graph will look like this, that here we will not write the line number. So, here we have, this is block 1, we have not written the line number here. So, this is block 1, and after block 1 block 2 will be executed, and here we have, if this condition is true, then we will go to 3, and 3 is this particular statement. So, this is just showing that if this condition is true, we will repeat, we will execute this loop block again. So, this is the self loop. So, this is a loop in this block. So, this is the way how we obtain the flow graph. Next is the DAG representation. We are discussing DAG representation for the purpose to just to optimize the instructions, just to optimize the code. So, here DAG stands for directed acyclic graph, directed acyclic graph, and this graph has no cycles. Now, it gives picture of how value computed by each statement in the basic block is used in subsequent statements in a block. Now, this DAG representation is used to determine common sub expressions. It can be used to determine the names that are used inside the block, but evaluated outside the block, and then again determining which statement of the block could have their value used outside the block. So, these are the certain purpose where why do we use DAG representation. However, there are other reasons also for using the DAG representation. I will gradually discuss in this lecture. First, I will discuss how we compute DAG. So, a computation of DAG is a DAG with the following labels on the nodes. So, here we will be drawing just tree like of a structure where there will be nodes, there will be edges, internal nodes, leaves, like that. So, just tree type of structure. So, here the leaves, they are labeled by unique identifier. They can be either variable name, variable name, constants. So, there will be the leaves. Now, interior nodes, they are labeled by operator symbols. So, the interior nodes will hold the result of temporary computation. So, they will be labeled by some operator, and nodes are also optionally given an extra set of identifiers for labels, and this gives idea of common sub expression, of finding or using the common sub expression where the particular node can be given, can be assigned the identifier for the set of identifier. Now, here we will discuss some code improving transformations. Actually, we will use DAG representation to optimize the code. So, for doing so, we can do some improvement in the code. So, some transformations will be required. So, just few transformations are written. We can eliminate the local common sub expressions. I am talking the computations or transformations that are performed within the block. So, this is that is why we have written local common sub expression, that is instructions that compute a value that has already been computed. So, if a value has already been computed and it is used at some another place also, mean the same computation is to be done at some another instructions also, then that computation is not required to be done again. The previous computation can be used in that place. So, here this is the elimination of local common sub expression. Second is the elimination of dead code, that is instructions that compute a value that is never used, mean there is a code that is never used and we have the code. So, that can be eliminated, that is considered as dead code. Next are reorder statements that do not depend on one another. Such reordering may reduce the time a temporary value needs to be preserved in a register. So, we can do the reordering. Next is we can apply algebraic laws to reorder operands of the tree address code instructions, sometimes thereby simplify the computation. So, here we can use some algebraic laws also to simplify our computation. So, we will see the example for each one of these transformation. So, first is the elimination of local common sub expression. So, what we do here, suppose we need to create a new node M, it is about to be added, the new node M, and there is already existing a new node N with the same children and the same order and with the same operator. So, we need to create a node M, but there is already node N with the same children and same operator and same sequence. So, rather than computing again M, what we will do, N computes the same value as M and may be used in its place. So, we can use it again. Now, see one example, suppose A is equal to B plus C. We already know how to draw DAG if we have A is equal to B plus C. So, see here in this instruction we will create the leaf node labeled by this one B and C. So, this is initial value, suppose B 0 and C 0 and result in A. So, this is the plus operator where we are performing the addition, and this is the interior node where we have operator, and this will be labeled by this identifier A. Now, next is A minus D, this updated value of A minus D equal to B. So, this is the updated value minus D naught, this is the initial value, and this will be equal to B now. So, here we will have minus and then we will write here B. Now, next what we are doing, B plus C is equal to C. B plus C is equal to C and B is updated here. That is why it seems that both are same, but actually here we have updated B. So, this B and this B is different. So, B plus C we will again compute B plus C. So, B and this is C, initial C, no change in C value. So, B and C they will be added and result will come in C. So, here we will write plus and C, right. Now, next is D is equal to A minus D. So, if we will see D is equal to A minus D, then here this A minus D and this A minus D, this is same, and before this statement value of A and D they are not updated. So, we can use this computation and this computation is same. Here variables are same, order is same, operator is same. So, here we can use this local common sub expression. So, on this node only we will label it with D also. So, just see here we are not labeling here C, rather we are labeling D here. Why we are not labeling C here? Because here it seems that the B plus C and B plus C are same, it seems, but it is value is different because B is updated over here. So, this is about the local common sub expression, and here we drawn the DAG representation. Using this representation we have eliminated, we can eliminate local common sub expression. Now, next is the DAD code elimination. So, in DAD code elimination we delete from the DAG any root or node with no ancestor that has no live variables attached. So, we repeated applications of this transformation, will remove all nodes from the DAG that correspond to DAD code. So, actually just see the example, suppose A is equal to B plus C, B is equal to B minus D, C is equal to C plus D, E is equal to B plus C. So, for this we can again draw the DAG representation, again the tree type of structure, B plus C. So, B naught and C naught plus operator and label is A. Next is B minus D, again we can use this B minus D and label will be B. Now, next is C plus D. So, C and D, this is C and this is D, operator is plus and label is C. Now, next is E is equal to B plus C, this B plus C, and here this B is updated. So, we need to recompute it. So, updated value of B plus C and result will come at E, result will come in E variable. So, this is the E label here. Now, here if we assume that variable E and C, they are not live, suppose they are not live. We just take the case, if they are not live, if E is not live, then we can remove this node, right. We can remove this node, and C is also not live. So, we can remove this particular node. And so, if we are having some variable that is not live, then that node and the corresponding nodes can be eliminated if that computation is not used in the block and in the subsequent blocks or in the coming blocks. So, this is known as the that code elimination. Next is the use of algebraic identities. So, we can use algebraic identities to eliminate the computation or to simplify the computation. So, we may apply algebraic identities like this to eliminate the computation. Similarly, we can do the reduction in strength, mean here we can use a cheaper operator in place of costly operator or expensive operator, like power operator can be replaced by this. 2 into x can be written as in form of plus, 2 by x by 2 can be written like using the multiplication operator. So, this is show that we can perform some reduction in strength by replacing the costly operator with cheaper operator. Next is, just see this example where we will do some simplification, like A is equal to B plus C, T is equal to C plus D, and E is equal to T plus B. Now, suppose T is not needed outside this block. If it is not needed, so we can eliminate this T, and what we can write, A is equal to B plus C, and in place of E we can write A plus D. Actually, just see, E is equal to what? T plus B here, and T is equal to what? C plus D plus B, and A is equal to what? B plus C, right. So, we can write here A plus D. So, we can write E is equal to A plus D. How we did this simplification? Just by using the laws, associative law, commutative law, we can easily do some simplification. So, this is a use of algebraic identities. Now, we can represent some array references also using DAG representation. Suppose we have x is equal to A of I. So, in this case, what we will do? We will use the operator like equal and square per bracket. Here we will write A and I, and that will be assigned, the value will be taken over here and it will be assigned to x, mean this is a label to this node. So, this is one first case. Now, next is, suppose we have a statement like Aj is equal to y. So, for this we will do here, this is a previous case, and here we will use the operator like this, and it will have 3 children. One is for A, second is for J, and third is for Y, and that will give the result for this node. So, he will create a node with this operator. We will create the 3 children for this A naught, J and Y, and there is no variable labeling this node. So, here there will be no label like in this case. Now, see here, suppose we have this statement, then this statement and this statement. So, here Z is updated, Z is taking the same value. Now, see here, we have the difference here, the creation of this node kills all currently constructed node whose value depend on A naught and cannot become a common sub expression. So, what is the meaning? If we perform this computation, then and here we are having the same Z is equal to this, because of this will be killed. So, we cannot write Z over here, rather we will perform this computation again, and this cannot be part of common sub expression. So, in this way, in today's class we talked about basic block. flow graph, next use information, and then we discuss the how we optimize quote or basic blocks using a DAG representation. So, we discussed DAG in detail. So, thank you so much.